Last hour we were discussing the viscosities measured in a capillary viscometer and the interpretation of that data in terms of aggregate properties. I'd like to continue that on. Recall, verified that the Bingham relation applied by plotting 1 over t against driving force, which is the head minus rho a over rho s over rho l u squared over 2g. And we found that the data plotted on a straight line with different lines for different concentrations. And we extrapolated, so perhaps this ought to be a dashed line, to an intercept value here from which we could calculate tau b. We had the Bingham shear stress. Let's see, to calculate tau b we need a zero, a reference. So if we put water in there, in this apparatus, we get something that looks like this. And this would be our zero, and this difference, then the difference in head would be the used to determine tau sub b. And then the slopes, the slopes would be used to measure calculate a to d. And we found that if we plotted the concentration, this is C1, C2, C3, and so on. We plotted the concentration against the a to d divided by a to l, where this is 1.0. That the data fit a straight line. This is log scale. Fit a straight line from which we could get k. And this led to empirical determination that a to d equals a to l. Kc. We then did a thought experiment and came up with a relationship a to d equal to a to l 2.5 for spheres times phi, from which we could say that these must be equal. Or that phi, the volume fraction, is Kc divided by 2.5. So from the slopes of this, we got a to d, and from that relation and the thought experiment, we were able to calculate the volume fraction. We went through this all last hour. I'm just summarizing it so that I can get a good start today. This term seems to mystify newcomers, so I'm going to elaborate just a little bit. This is the volume of particles, which might be aggregates with the water incorporated between the internal particles, divided by the volume of the suspension. That is a whole. If you have a glass full of suspension, then it's the volume of the particles in the glass divided by the volume of the glass. It's another way of putting it is volume concentration. It's sometimes called volume concentration. So knowing that volume concentration, we then can calculate the density of the aggregates from the relationship that density aggregates is equal to C over rho P times volume fraction of the aggregates times rho P minus rho L plus rho L, where this is the density of the water in the pores, and this is the density of the particles. This C over rho P is equal to the volume fraction of the particles. I'll call it phi sub P. This is grams, that is, if you use the right units. This is grams per centimeter cubed concentration. This is grams per centimeter cubed mass concentration. Mass concentration. This is the density of the particles, density of the liquid. And for seawater, this is typically 1.025 grams per cubic centimeter. So if you put concentration and density in grams per cubic centimeter, or whatever units you use the same units, then you can calculate the density of the aggregate. I'll just give you this. It's derived in the handout I passed out earlier. Phi A and phi P. This is the density of an aggregate, which might be a bunch of particles. I'll draw it in 2 dimensions. Might look something like this, where the particles are actually touching each other. Summarize it like this. This is the phi sub A, and this in here is phi sub P inside the aggregate, or inside the volume. Okay, with that kind of build-up, let's take a look at table 4 on page 24 of the report. The column 1 is the name of the source of the samples. They were shipped in from these various harbors where there are or were serious sediment problems. And I might point out that Gulfport Channel and White River were Montmorillonite sediments. They're practically pure Montmorillonite. Brunswick Harbor had more kaolinite, and San Francisco Bay you've already heard about. It's a mixture of the 3 samples. But you'll see that White River and Gulfport Channel will stand out in their properties. K1 is this K, K1 in the report is the slope of that line. And you can see that they're quite varied. They range from about 6, a little under 6, well, the Potomac River is at 3.7 to a high of 11. So there's quite a bit of difference in the slopes of those curves. Then the next column is C over rho F. When this was written, we called them flocks. I like to call them aggregates now because flocks are confused with such things as aluminum sulfate precipitate, for example, aluminum hydroxide. And all through here you'll see the subscript F for flock, but let's call them aggregate. So it's the concentration of, let's see, by weight of the particles in the flocks. Then the next one, phi sub P over phi sub F, is the fraction of the volume of the flocks that's occupied by particles. Do you follow me? And if you look at that, notice that the fraction occupied by particles is quite small. It's on the order of 10 to 20%. Well, there's 25%, which means that the remainder, 75 to 90%, is all water. So we're talking about a structure that's mostly water. Looks something like this, with particles stuck to each other, but in training incorporating a lot of water in the aggregate. As you'll see later, these are the most dense of the aggregates. So you can appreciate the fact that the water content is very high in aggregate. Then the final column is the density, the bulk density of the aggregate. That is the density of the entire aggregate. Notice that it ranges from about 1.16 to about 1.4, almost 1.5 grams per cubic centimeter. That's the density of mud deposits on the bottom. Deposited consolidated material has densities about like that. So we're talking about the most dense of the aggregate. And the reason that we have dense aggregates under these circumstances, it could be that they just weren't broken up, when they were put in the viscometer. But actually, it's because only the dense ones could survive in the high velocity gradients that exist there. Velocity gradients in the capillary viscometer range from about 100 per second, 100 centimeters per second per centimeter, to about 1,000. And they, of course, occur at the wall of the viscometer. These are very high velocity gradients. We'll talk about them later this hour, about the velocity gradients that exist in estuaries. But these are high velocity gradients, and only those aggregates that could survive. And remember, tau B was the mechanical shear strength. So undoubtedly, we had them forming and breaking and forming and breaking continually in the viscometer under these high velocity gradients. Well, knowing the volume fraction of the suspensions that we used for the measurements, then we could calculate what the volume fraction would be to fill the whole thing up, that is, to make it 1. And using the relations for shear strength, for Bingham shear strength, shown on the figures 8 through, page 26, figure 11 through 17, which were linear, we could extrapolate the volume fraction for the shear strength, or the shear strength relation, to a volume fraction of the aggregates equal to 1. And that would give us the shear strength of the aggregate itself. Do you follow me? Anybody have any trouble with that concept? So it's an extrapolation. Okay. We know the volume fraction of the aggregates in these measurements, right? And these simple linear plots could be extrapolated to the volume fraction, or to the concentration. These are in concentration. To the concentration where the volume fraction would equal 1. So in other words, the whole viscometer was full of a flock, if you like. And that would be the shear strength of the aggregate itself. In terms of its Bingham shear strength. On page 36, there's another table that shows the Bingham shear strength in dynes per square centimeter for each of these harbors. And you recall, I'll digress just a minute. Recall that you can describe surface tension of, say, of a liquid, say water, as so many dynes per centimeter, or the energy to increase the area of the surface as so many ergs per centimeter squared. So we have dynes per centimeter for surface tension. Is a surface tension, or you can multiply this, dyne centimeters per centimeter squared. It's the energy required to increase the area of a surface. By analogous reasoning, we can say that the shear strength of the aggregates has the units of dynes per square centimeter, or dyne centimeters, ergs, per cubic centimeter. In other words, to completely disperse an aggregate, a primary aggregate, zero-order aggregate, takes this much energy. You all follow the argument? So we can say in the second column on table 5, that these numbers are the shear strength of the aggregates, or the energies necessary to disperse the aggregates. And these are primary aggregates, remember, just aggregations of primary particles. And it ranges from 11 up to about 46, 49, up to about 49 dynes per square centimeter. Doesn't sound like much, a dyne is not a very large unit of force, but it's large compared to such stresses the particles are subject to in the water. And the following column is energy of cohesion in terms of dyne centimeters per gram. That's not so important as the second column. On the I might say that these are comparable to shear strengths of channels dug in a cohesive soil. If you want to consider the surface erosion of soil, of a saturated soil, cohesive soil, that's about the shear strength that you would expect. Typically 5 to 20 dynes per square centimeter for cohesive soil. So we're talking about a dense, further evidence that these aggregates must have been dense, strong aggregate. On page 33, there's a plot showing the effect of salinity on shear strength. And notice that they tend to rise and then plateau. There are only 4 sediments shown here. But they tend to rise and plateau, and the values way off to the right are, you can see the bottom ordinate is broken there, are at high salinities, 20 grams per liter and 33.8 grams per liter. And you can see that the values are comparable. It appears from this that at about 1 gram per cubic centimeter of sea salts, most of the cohesive properties are fulfilled. That's something a little more than 1 gram per centimeter. Again, supporting the observation we made earlier when we talked about cohesion, that it doesn't take much sea salts to make the particles cohesive. And then finally, I'd like to point, in talking about viscometer data, to page 37. There's a plot showing the cation exchange capacity, or the shear strength of these aggregates plotted against the cation exchange capacity. Now that's useful because it's a job to make these viscometer measurements, but it's easy to measure the cation exchange capacity. So it's a useful index of the shear strength. And let's see, I have a that plot can be plotted as a linear plot, and it turns out to be tau b is equal to 3.9 plus 0.845 times the cation exchange capacity. And that fits these data with a root mean square deviation of 4.5 dynes per square centimeter. Or r squared equal 0.9. Not a great fit, but strong enough to make it useful. Okay, then to summarize then, from the capillary viscometer data, we were able to calculate the densities and the shear strengths of these aggregates, and we found them to be quite dense and quite strong. And these measurements were made in very high velocity gradients. Now, there's two other problems with the capillary viscometer that I mentioned earlier. One is the velocity gradients aren't uniform in the viscometer. In a Newtonian liquid, the velocity gradients range from a very high value at the wall to 0 at the center. In the Bingham fluid, it ranged from higher viscosities, higher velocity gradients at the wall to 0 at some point just inside the wall because of the plug-like motion near the center. So we're dealing with very high and probably variable velocity gradients. Secondly, the dimensions of the viscometer are small. It was like half a millimeter, if I remember correctly, in diameter. So aggregates larger than a half a millimeter, or larger actually than some small fraction of that half a millimeter, couldn't really be accommodated in that instrument. So we're dealing with small aggregates too. In order to overcome that, those problems with the viscometer and to study the other structures in the viscometer, we needed an instrument that would provide nearly uniform velocity gradients and that had appreciable dimensions so that larger aggregates could form, and we surmised that the effect on the walls would be less. That is, if you have a larger volume, the effects on the walls would be less. So we created a device. There's a diagram on page 40 in your handout. A device that consisted of a 1 liter graduated cylinder with a glass tube down the inside of it so as to make a 1 centimeter gap. Graduated cylinder is about 6 centimeters in diameter, and so we had a 4 centimeter diameter cylinder in the center of that. And this cylinder was mounted on a hollow tube connected at its end so that it could be held in a concentric alignment with the outer graduated cylinder. And that tube was positioned by 2 air bearings. Friction would prevent accurate measurements, so we had high pressure air jets impinging on that tube so as to keep it centered but not keep in contact with the wall. And at the top end of that piece of tubing that supported the inner cylinder was an aluminum plate fastened rigidly to it and small magnets placed under the plate, just like the damping magnets in a analytical balance that dampened the rotation. As the plate passed by it, it created eddy currents in the aluminum plate, which provided drag because it short-circuited eddy current. And it was a very effective damper. Also mounted on that plate was a small mirror onto which could be projected the image of an arrowhead. And this arrowhead was fairly small, and it reflected onto a wall about as far as from me to the wall here, so as to provide a long light lever. And there was a piece of tape on the wall that you could use to zero the light spot out there. So you had amplification, virtually noise-free amplification, by the way. There's not much noise in that long light arm. So that the position of that inner cylinder could be determined fairly precisely. The entire inner cylinder was supported by a torsion wire that is a stainless steel, like piano wire. I've forgotten the diameter, 10 or 15 thousandths diameter, that was more than a meter long, so that it took very little stress on the surface of that inner cylinder to twist that wire. The top end of the wire was fastened to a micrometer dial, which could be positioned to within a thousandth part of a circle and read to within a thousandth part of a circle. The procedure in using this was to put a known amount in the graduated cylinder, lower the whole apparatus. It was on a framework that stood about this high. You could raise it up and lower it into the graduated cylinder and determine the zero position of that light spot. And in fact, it was rotated so that it had a zero position. Then the outer cylinder, which was mounted on a phonograph, like a phonograph turntable with a variable speed drive, start rotating the outer cylinder, turn the dial until the mirror was brought back to the zero spot on the wall, so as to compensate the torque in the inner cylinder. And then from that, you could calculate the stress on the surface of the inner cylinder for the given rotation. You follow me? Now, the nice part about this instrument is that, nice parts about it are that the gap between the two surfaces is fairly large. Even with that large gap, the velocity gradient didn't vary a great deal. I think it was about 2 to 1. I've forgotten now, but something like that, inner and outer cylinder. And the inner cylinder could be lifted out as necessary, and a plunger run up and down if you wish to mix it vertically. There was a problem with it settling, although it turned out not to be nearly the problem we anticipated. And then we could measure very sensitively. It measured down close to a dyne per square centimeter, which is pretty good. The disadvantages were that the top and bottom ends of the sheared fluid were asymmetrical, and secondary currents would develop if the velocity gradient were too high. We operated below that. The bottom of the inner tube had a rubber stopper mounted part way up, so that there was just air there. There was no bottom surface on it. Okay, you all see what's going on here? Now we can deal with this quantitatively. I'll redraw parts of it here. I'll leave that out. We have a length. I'll call it H, a height of the shearing region. We have R1, and R2, outer cylinder radius. And this is mounted on a turntable. It could turn at some rotation rate in, let's say, revolutions per minute. And then we can measure the torque on the inner cylinder. Now Bingham's relation for this circumstance, I'll draw a top view of this, enlarged top view. At any distance out r, the tangential velocity we'll call q. At any r, between r1 and r2. We can write Bingham's relationship tau is equal to tau b plus eta sub d times dq dr minus q over r, where this takes out the fact that it's rotating and lets us look at it like a still picture. So for Bingham's relation, we now have this one. And for the torque, T, we can write the 2 pi r squared, that's the circumference of the cylinder where the rotation is taking place, times h times tau, the shear stress on the inner cylinder, or on the shear stress at that point in the fluid. See, I'll call this relationship 9. And this 10. So if we substitute for the tau up here, we can now write eta and rearrange it a little bit. We can write eta sub d times dq dr is equal to the torque divided by 2 pi h r squared times eta sub d omega. I'll call it omega 2. That's the rotation rate of the stop. This is still, so this is omega 2. How do I write that? Yeah. Rotation rate. Omega is equal to 2 pi n. It's the angular rotation rate. Okay. Omega 2 plus 4 pi h times the natural log of r2 over r1 divided by 1 over, wait a minute, I've got something wrong here. Let's start over again. Eta sub d times dq dr is equal to t over 2 pi hr squared plus eta sub d times q over r minus tau b. Okay, now I'll get to the next one. If we integrate this, we can write the torque, and solve for the torque, is equal to eta sub d times 4 pi h divided by 1 over r1 squared minus 1 over r2 squared times omega 2 plus, here we are, 4 pi h log of r2 over r1 divided by 1 over r1 squared minus 1 over r2 squared, all times tau sub b. So we have a nice linear relation. For any concentration, we have an eta sub d. All these terms are constant. So we have the torque is a function of the angular rotation plus tau sub b. Y equals mx plus b. So we have in our apparatus now what we actually put into the machine is N, or RPM. And we measure a dial reading. And the dial reading is, this is proportional to N. And the dial reading is the torque. So for a given rotation rate, we get a point, and an increased rotation rate, we get another point, and so on. You follow me? This was a long, tedious process, measuring all these points and setting the light on the wall. Well, that seems simple enough. We ran into some problems right away. You look on page 48, you'll see some data from one such experiment. Let me describe each of the sets of points for you. The little pluses that you see were values read when it was first started up. And this is Wilmington district sample. When the instrument was first started, the first reading at a rotation rate of something like 8 revolutions per minute was shown by the first plus. Then you can see with successive increases in rotation rate, the pluses stayed about the same. What's going on there? Any ideas what's happening? Aggregation? It was breaking up the structure of the material that was in there. In other words, as you increase the RPM, you just broke up more of the material, so that from being a stiffer material at first, then you were getting less and less. At about 42 RPM, the apparatus was stopped, and a plunger was run up and down. Then it was started up again, and the next one is shown by the X, and you can see it's a little bit higher. Must have broken up some more of those aggregates. And then it similarly just leveled off. Increasing shearing rates just broke up more and more material. Well, if you let it run at the highest, about 180 RPM, for some time, then reduce the RPM. Let it run. If it's breaking up the aggregates, then you better let it break them up for a while. Then reduce the RPM. The next point is shown by the circle, next on the rightmost circle on the plot. And then reducing it further was the next circle, and then going down in successive values, you can see it's beginning to look like a Bingham plot. In other words, we'd broken it up enough and it seemed to have some kind of an aggregate structure in there. The apparatus was stopped about where that little arrowhead is shown, and the plunger run up and down. The inner cylinder lifted out and the plunger run up and down to see if that had any effect. And it was started again on the square. The next square shows that it still falls on that same line. Apparently the structures, whatever structure there is there. And the next square is still on that same line. So we have at least a portion of the plot that looks like it fits a Bingham relation. The next one, though, is off that line, indicating that something's wrong. So the apparatus was stopped, the inner cylinder lifted out, and the plunger went up and down again 10 times. Then it was started again, and the next value was read where the triangle's shown there. And then you can see it too follows a Bingham relation, but a different one. This is a kind of a puzzling circumstance. Unfortunately or fortunately, depending on your point of view, this was observed for all the sediments, this kind of behavior.
When there's an upward jump in the dial reading, that means the torque increased. Is that right?
It means the torque increased, that's right.
Which meant that viscosity of the suspension went up.
It means the combination of viscosity and breaking up went up.
Breaking dispersion of the particles, so it's a more uniform solution rather than individual particles in water, which has a lower shear strength.
Remember, the shear stress, which is proportional to the dial reading, right, is the sum of the mechanical and the viscous part. So we have the mechanical part has to do with the frequency with which bonds are made and broken apart. And the viscous part has to do with the volume occupied by the aggregates. In other words, the more volume there is, the steeper this curve should be. The slope of the curve is related to eta sub d here. So the greater the volume occupied by the aggregates, the steeper the curve should be. And the intercept indicates this tau sub b, the strength of the aggregate.
So you're saying as the aggregates break up, there's a greater volume of the aggregates?
The aggregates, visualize the aggregates as colliding with each other in the velocity gradient. And each time they collide, they may stick instantaneously and then be torn apart again. Okay, otherwise you wouldn't be measuring any mechanical strength. So this mechanical strength, if you like, can be likened to an impulse momentum type thing. You know, the force of rain on the roof. You know, each drop only hits instantaneously, but the sum of all the drops produces what appears to be a force on the roof. Same thing as gas molecules striking the wall of a container. That creates a pressure. So you can look on this as the same kind of it's a process of colliding and breaking and colliding and breaking. Well, this observation, the fact that it occurred with all the sediments, the same kind of an operation, made it appear that you didn't really learn much from the increasing RPM, because that was just breaking up whatever structure happened to be there when you filled it up, which is more of a fairly strong structure. I'm going to talk about that later as a separate thing in terms of gel. But you could learn a good deal about from the decreasing RPM fractions of the curve, where it fit Bingham's relation, and you could separate the two, the fluid and the mechanical part. Y'all follow the observation there?
When you say you took the cylinder out and ran a plunger down into it, I'm trying to understand what you're doing with that plunger.
Oh, the plunger is thanks for reminding me of that. The plunger was just a ordinary rubber stopper mounted on a glass rod, or a piece of glass tubing. It was sealed at the bottom end here. And the purpose was to cause the material to mix thoroughly. It was a high velocity gradient circumstance. But when you pull it, and it was run up and down, mix thoroughly and make it uniform from top to bottom. Same thing you do in a particle size distribution analysis. But it had the features of leaving a decaying bunch of eddies in there, so that whatever would aggregate could aggregate after that. That's an important point, because you notice in this first straight line, we could stir it and it still came back to the same line. So whatever structures existed in that system were stable under that, within that range of velocity gradient. Now, you can't see much on this one, but you actually get another one up here on the top, and most of them, another velocity gradient. And occasionally you get a strange one down there, but most of the time it looks just like this. Using the same analysis we used before, we now have concentration. We did this for the same kind of experiment for successive concentrations, a wide range of concentrations. And we could plot from the slopes of those curves A to D over A to L on the log scale. And we would get, for that flatter curve up there, a slope like this, and for the steeper curve, another slope, and typically we'd get a third one. So we got at least 3, and sometimes we got more of these individual slopes. And from this, we can calculate a volume fraction. I'll call it V1 from this slope. V2 in slope. V3. So we did that before, you know, from the volume fraction is equal to K1 C divided by 2.5. So for each of these slopes, we could calculate some kind of a volume fraction. And similarly, from the value of tau c, which came from this part of it, the intercept of those curves with the axis, the extrapolated curve to the axis here, we could calculate a shear strength for the suspension. And we'll talk about the shear strengths a little bit later. But here you can see we've got different structures, evidently different structures that are smaller and stronger, shown by the curve with the flatter slope here. And in fact, the slope is flat means that the volume fraction is less for the same concentration, same mass concentration of suspension. Sediment concentration, 0.112 grams per cubic centimeter. For that same mass concentration prevailed throughout this range of velocity of RPM. The change in here indicates that the arrangement of those particles were such that they occupied less volume and were stronger in this flatter curve than they did in the steeper curve. That is, more volume in the steeper curve than the flatter curve, and weaker. So we have a problem here that I should put it another way. We have information here that indicates a change in structure over different ranges of velocity gradients, and we need to know what that structure is. Well, I proposed the following scenario, or structure arrangement, to explain this. Remember, we had a system that we could virtually control everything except what happened as a result of the velocity gradient. Suppose that there existed in a suspension a lot of individual particles, individual mineral particles, and that they're brought together in a velocity gradient and form an aggregate. Okay? And we'll call it the primary particle aggregate. Okay, so we have a whole lot of primary particle aggregates. These would be strong, fairly strong, let's say at the strong end of the scale, because they're mineral particles all stuck to each other in some kind of a structural arrangement. Now suppose that we had a lot of these primary particle aggregates in suspension, and they were brought together. So that we'd have, in this case, something that looked like this. And if we had a lot of those in a suspension and they were brought together in a velocity gradient, then we could have an aggregation of those, right? Where we have a particle aggregate. I'll put it simply like a particle aggregate so we could have an aggregation of particle aggregates. And that might look something like so that the aggregate now would be look like that in 2 dimensions. And I'll call this a particle aggregate. You can see that the each of these particles, the primary particles of which the aggregate is composed, has the density of this kind of an aggregate. But now we have additional pore spaces between the aggregate, between the primary aggregates in this aggregation of particle aggregate. So that the density would be lower, or put another way, the volume fraction would be greater. The bonds between primary particle aggregates are actually the particles in the aggregate bonding with particles in the other aggregate, right? I mean, it's the mineral particles that bond to each other along this, but because the interface between these particle aggregates is limited, then you'd expect this whole structure to be weaker than the previous one. Okay, using that same argument, suppose that we had a lot of these in suspension, and we reduced the velocity gradient so that they could collide with each other and form aggregates, then we would have aggregates that looked something like this, which again would have pore spaces between the aggregates. Each of these has the aggregates inside of it. This one up here. It would have still lower density. Still lower density than this one had, would be weaker because now we would only have the contacts between these individual particles in the adjacent ones that contacted. So we'd have still less strength and lower density or greater volume. So we'll call this a particle aggregate. Okay. You get the idea. In order to save ourselves some confusion, let's call this a 0 order and this a 1st order, or a primary particle aggregate, and this is a 2nd order. Aggregate. Okay, so with this kind of a idealized, if you like.
Established that equation there,
This one?
or basically the mechanism that we use, right? And how does that equate to the diagram that we get? Does it equate to either one of the 2 lines, or is it useful for the diagram, the equation?
Well, the plot that I showed you refers to this equation. Here. The dial reading is the torque on the ordinate of that, and the abscissa is the RPM, okay, and that's related to omega 2. So we have y equals mx plus b. It's just a linear relation. So for, rather than reduce every point and plot it in this form, plot it as a direct data from which you can calculate from the intercepts and the slope directly this parameter and this parameter.
And is it, does coincide pretty well with the diagrams?
What's that?
The information there doesn't coincide pretty well with the diagrams, so that the experiment, this is like theoretical, right?
This?
Or maybe I'm not understanding. The equation itself there is basically giving us theoretical value.
No, it's based on this. The only theory is this one. The rest is just calculus and algebra, in geometry. The assumption is the same one we had before, that the shear stress in the fluid, at any point in the fluid, is the sum of a mechanical part and a viscous part, and that we can superpose them. That's the only theory up to this point that I described so far. And this just reflects the geometry of the apparatus, the dimensions of the apparatus, and the torque. This is just substitution of this into that, and then this is the integral of that. So there's no theory except this. It's important to keep in mind.
I think what he's asking is, did that match the curve that you got? And the curve that you got obviously had several different.
Oh, yeah. It has several. I see. I'm sorry, I didn't get your question. That's right. At least over this range where there are straight lines, it matches the theory. It doesn't match the theory in the increasing part, because the viscous part and the mechanical part were both changing. That is, the structure was being broken down. So it only works when these two terms are constant, from which we can say that the Bingham's relation applied for the straight portions of these, but not otherwise.
Those two terms change if the slope of the line, right?
I
Those
did.
two terms up there change if the slope of the line.
If tau b and a to d change, then it's not going to be a straight line. It's unless the unlikely circumstance that they compensated each other in their change or something like that. But the theory only holds on the straight line portions. That's the reason for spending so much time on this, is to indicate it seems to fit here, and during that portion there must be some kind of structure, and we need to figure out what that structure looks like, or get some kind of an explanation. Otherwise we're dead in the water. We can't explain it. So we came up with this second step in the theory, if you like. Maybe within these velocity gradient ranges, remember velocity gradients were nearly uniform in the annular space. Within these velocity gradient ranges, one structure seemed to be stable. And the fact that a succession of such structures appeared repeatedly meant that there must be different structures which are stronger and have less volume fraction here than they do in the adjacent one. So this theory was cooked up, was proposed.
Let me ask you a question. You have the equation here and you need to find tau b. Did you get the differential viscosity from those earlier curves? You showed it right behind you. Did that come from the earlier curves?
No, it came from these curves, from this curve we just looked at, from this.
Okay, I've got the dial reading on there, but I don't see where
Okay.
the differential viscosity came from.
There's the slope, from the slope of the curve. See this? This is the slope here.
Right.
from the slope of that curve, we know all these terms in here. These are all fixed here. And this is the ordinate there. So that, I'm sorry, this is the slope here of the curve. Okay. Omega 2 is the RPM, is proportional to the RPM. It's omega 2. So we know we varied the RPM and we measured the torque, and then we plotted that for different RPM so that we could get from the slope this term, and this is just a number here, okay. We know the RPM, so whatever the slope was, it was the slope divided by this number gave us this.
And then you take that, all that was left was tau B.
And then the intercept, from the intercept on that curve, divided by this number gave us tau B.
I have a question. Given that this is now postulated as the reason for the
Different.
various slope with the shapes of those curves, how is that going to impact the use of the cation exchange capacity for sort of estimating?
Can I save that till Tuesday? Because there's some explanations in between, and we'll come back to that. Obviously, the shear strengths of these other structures won't be as strong as those structures were, whatever those structures are, dense, small aggregate. And these, now we have larger aggregates, and we have different ones appearing. So it appears that these are less strong, that is, that they wouldn't affect that. Well, this is a nice simple description of some aggregate structures that has to be verified before we accept it. If we go on to it, though, I'd like to point out that if you look at the square symbols in the decreasing RPM, the last square symbol toward the origin is below the line, which means that if we just, and if we found, if we had just continued to decrease RPM, that would have curved down until it became asymptotic with the other curve. In other words, there would have been some kind of a transition in there. But we stopped it and replunged it, gave it an opportunity to get to the next curve. We're doing that with an experiment that really controlled all these things. It didn't just allow it to continue on to the next curve. And you'll see in the literature lots of plots where they actually just go down, continue going down, and it becomes asymptotic with another straight line. And they, of course, that's what you see if you don't wait, provide an opportunity to stop and let them form.
Did you let it go down to almost 0 RPM and then start it up again? Or did it trace out again?
On the next page, it shows it. Yeah. Page 50. You can see that, well, let's see, the increasing one were the circles. I'm having a little trouble remembering. If I recall correctly, the lower curve, the first one, and the increasing RPM were the plus, X, and triangles. The plus goes up a ways and levels off, and then it was stopped and suspended, and you can see the X curves, and then it was decreased, and it followed the relation that we discussed earlier. Then it was increased again, and the next one was let's see, the next one must have been the triangles. Yeah, the triangles, and you can see they went way up and mixed it. High values, and then as they broke down, they came to lower values, and we came back to that same kind of a relation again. In fact, they're just parallel to the preceding one, but now with a higher shear strength. So apparently, with repeated shearing, you could get changing values, changing structures. As you broke it up more, then you had more pieces to form new aggregates. what we did after we discovered this and first starting it was to let it run a long time at 180 RPM until it broke everything down, because you didn't get much information out of this, and we were interested in this other. Well, in order to justify this kind of a structural arrangement, I'll have to make some further assumptions and some computations. Looking at the picture over there, we can say that the voids, are you all familiar with void fraction in soil mechanics? It's volume of voids per volume of soil. Okay, we can write the void fraction between the particles in a particle aggregate is equal to the volume fraction of the particle aggregate minus the volume particles, right? All divided by the volume fraction of the particles. And we can write the void fraction between the voids created by the last aggregation step is equal to VPAA minus VPA divided by VPA. We'll make the assumption that the water assume that rho L, the density of the water, is constant. That is, it doesn't change the density. It isn't different. It's not different in the pores from that outside the pores. So when we put it together, it doesn't change depending on the spacing of the particles and so on. And that the rho P is constant also, that their density doesn't change. Now remember, we talked about expanding lattices and so on. We're assuming that whatever expansion took place, it's already done. We've already eliminated that. I'm going to talk later about density of the liquid next to clay mineral surfaces, and it turns out that right close to the surfaces, its density isn't the same as the density. It's lower than the density out in the liquid. But we're going to, in order to make this computation, we're going to assume that it is constant. And actually, it's lower very close to the surface. So on the scale of the particle sizes, this is probably not a bad assumption. If we do that, then...
I don't understand the difference between the notation on the void ratio, where you have your parentheses. On the first one, you have parentheses around the P, and then you have AA. I don't understand.
Okay. Okay. But what I want first is to know the void ratio for these voids. And in the second case, I want to know the void density for these voids. So I just put the parenthesis to indicate that the part within the parenthesis we'll consider as a particle, as a solid particle. So then we can write, from these definitions, we can write volume for any, I'll say VNA, is equal to minus the volume fraction of the particle is equal to VA minus VP plus, put parenthesis around this, plus VAA minus VPA, and so on. in other words, just sum up all of these voids, and finally to phi na minus phi n minus 1 a. Combining these,
Question, just looking at the symmetry of what you're doing here, why in that first term wouldn't you have, instead of phi sub p, phi sub pa, both the numerator and denominator? I guess, I mean, it
Why-
seems
why
like
is-
what you're saying there, you're looking at the first order, wouldn't you be comparing everything to the order below it? And then if that's the case, then you've got a first order, and wouldn't you be comparing that with a zeroth order, and wouldn't that then be VPA?
yeah, well, what we're saying is that the total difference, this last statement is that the total void space in the aggregate of whatever order it is the sum of this void space here plus this void space here plus the void space in here.
Yeah.
We're just summing it all up.
I guess I,
P in front of the first, after the first P there, the next word.
No, BPNA. No, next equation.
Next
Next
word,
panel.
next panel over, next panel.
Panel, this one.
to your right, part of,
Up here,
Is that the first term,
PNA for any number.
Okay.
This is N. I could write, oh, I see, P. Yeah, thanks. Yeah. PNA for any number of orders of aggregates. The highest that was observed was 6, up to 6. But that's pretty fluffy stuff, you know. Okay, so with the definition of these definitions here applied to this now, we can write phi n a is equal to phi p a plus the void ratio for p a times phi p a plus the void ratio for p a times phi p a plus and so on. And phi by plus 1, each step in this thing, is equal to the void ratio of I at I plus 1 times the volume fraction of I. Or put another way, we can write E sub I is equal to E sub I plus 1 is equal to epsilon sub I divided by 1 plus epsilon sub I. Now there are a bunch of assumptions that follow, and they're on page 67. I hate to stop this right in the middle. It assumed that the primary aggregates retain their density during aggregation. That is, they don't change their density. And it assumes that there's no significant rearrangement of mineral particles in the aggregates as they combine. That is, they don't collapse or anything like that. And that successive aggregations beyond beyond this one, that is, in each of these aggregations has the same amount of intermeshing. If you follow me? In other words, if they aggregate, the individual particles in them have to intermesh a little bit. And that it's the same, that we can regard each one of these steps as being like the one preceding it. That's not an unreasonable assumption. And then with that, we can write we can combine these and write, come over here, epsilon I vi equals epsilon I plus 1 vi plus 1. And all of this, so all these terms collapse, and we have phi p n a is equal to phi pa, the primary particle aggregate, plus n minus 1 times epsilon sub I times phi sub I, where n minus 1 is the order of aggregation. And this can be simplified further to phi n a is equal to phi a times 1 plus n minus 1 times epsilon sub I. The important thing to observe here is that because of all our assumptions of similarity in each step, that the volume fraction for any one of these orders of aggregation depend on the volume fraction of the primary aggregate, something you would have concluded from intuition, I think. That is, depending on how this is structured, all the rest of them have structures. I put it backwards. All of the structures of all these depend on how this one is structured.
The last step is basically making the assumption that
This one?
Yeah, from there to the next equation is assuming that EPA is equal to
Well,
I.
if you put EPA, epsilon PA, phi PA here, then it collapses to this. Oh, wait a minute. Do I have E1? This should be 1. Thank you. The first order, yeah. I've kept you late, folks. I'll make up for it next time. We'll quit early. We'll see you on Tuesday.
I guess I'm still confused about this in comparison with the diagrams, the hierarchy here. It would seem like the first one, this minus, you would want to start with.
Yeah. Well, these are what we started with.